last time, to give today a short overview of what is called least squares methods. This is a topic on which you have heard quite a lot during your studies in different areas of applications. So I will today give some overview covering many different aspects of this problem and different applications. So let's start with a simple example. And this is linear regression. We have a plane, we have some points, and the question is how to fit the straight line y equals ax plus b in the best way to those points. Let the coordinates of those points be x1, y1, and so on, xn, yn. Then the plump thing would be, well, let's solve the equations. axi plus b equals to yi. Well, this would be solvable if the points would lie already on a fixed line. Then you will be able to solve. But otherwise, this is impossible because you have more variables than equations. So the idea is, let's find a line for which the differences of those distances be smallest. Well, that would means to make, well, for example, max over all i's axy plus b minus yi be minimum. Or you can say, well, let's make a mean value of them, sum them up. So that would mean then sum over I axy plus b minus yi the minimum. The disadvantage of both of those approaches is that they are very difficult to compute. Although they are not to be neglected, both of them. Rather, Gauss proposed the following. Let's make this to be smallest. Square them, then sum up. All three approaches have one thing in common. If the points lie on the line, then they are zero, all of them. So for each of them, the left-hand side is a measure of how far you are from a line. You may have quite bad points where no line would be good with any of those criteria. But anyhow, so you would always expect that your points are such that this asking has a sense. This, it would have no sense. Okay. So, if I now put some matrix notation, G equals x1 to xn, 1, 1. Then Z is equal to AB. Then GZ minus minus Y is equal to AX1 plus Y plus B minus Y1 and so on, AXN plus B minus YN. That's what it is. So now this expression now is equal to GZ minus Y norm squared equals to minimum. Which we can write down as ZT GT GZ minus 2 ZT GT Y plus Y squared as minimum. Now this is a constant, so in looking for minimum it is irrelevant. So those two terms are of importance. So this is a quadratic function which we can write down as 1/2 A Z minus Z B equals to minimum. Well, this B shouldn't be confused with this B, okay? This now is a vector. Where A is equal to GTG and B is equal to GTY. So this GTG is automatically symmetric and positive semi-definite. This expression AZZ is always greater or equal than 0 because of this form. But the question is, can it be 0 on non-trivial vectors? When G x equals to 0 means GTG XX equals to 0. I am now using the common notation for the scalar product. And that means Gx equals to Gx norm squared equal to 0. And this is equal to 0 if and only if Gx is equal to 0. So now look, when gx is equal to 0. Oh well, excuse me. I have made some confusion, but not confusion go too far. So, so what that means? Is there any vector which is sent to 0? If this is equal to 0 for all of them, what that means? That means AEXY plus B equals to 0 for all J. Well, that means that all x's are equal. So your points stay on a vertical line. That should be excluded. But if in any other case you have positive definiteness here, and this will have always a solution. So this is a theorem, now quite general. Let A be definite symmetric. Then A z 1 half minus zz equal to minimum if and only if b is equal to a minus 1, z is equal to a minus 1b. You have to solve. You differentiate this equation with respect to z and you get this equation immediately. You differentiate this with respect to variables z, and then you get just a z equals to b. That's a short, that is a sketch of the proof, but that's not the proof. Well, in the proof, we will now go much more general way. We will suppose that the space in which we are working is not just an Euclidean space of vectors, of n-dimensional vectors, but just any Hilbert space which has a scalar product. And a more general situation, more general. We should have then reformulate this theorem according to this more general proof, but that's easy for you, more general. We take X to be a Hilbert space, and A are self-adjoint operator in X, which is positive definite. Then, well, that's our additional, more general assumption. It includes the matrix formulation, of course, in a finite dimensional space. But a self-adjoint operator on a Hilbert space which is positive definite means that A is defined on some dense subspace of A and maps is in X. A Z T is equal to Z A T and A Z Z greater or equal than 0, Z unequal to 0, and the inverse is defined on the whole space. That means that the range of A is everything. This is not an orthodox definition of a self-adjoint operator, but it's correct in this special case. In fact, we know that in this case, the operator A is in fact positive definite. That means that AZZ is greater or equal to 10 delta squared for some delta greater than 0. But we will not need this in this simple proof. See, in the finite dimensional space, this inequality is equivalent to this one. Not so in the Hilbert space. But yes, if the inverse is defined on the whole space, an additional supposition. So now let's prove. The assertion and the proof is quite simple, it's just algebra. So, the equation A x equals to B has always a solution because the inverse is always everywhere defined. So x equals to A0 is equal to A minus 1B. That's what's known. Now set x to equal x0 plus h. And now we look at A x0 plus h, x0 plus h, of course also from d of A. Then h is also from d of A because d of A is a linear space. This d of A, well, I didn't say, but it is automatically so. The means of definition of linear operators are always linear spaces. Not all space, but some subspace over the Hilbert space. So, now, this is now equal to 1/2 A, yes. So, yes. Minus x0 plus h, x0 plus hb. This is equal to 1/2 A x0 x0 plus 1/2 x 0 a x0 h plus 1/2 h x0 plus 1/2 h minus x0 tb minus hdb. I just wrote down what it is. Now, because I know this, then I know that see, this is equal to this because we are in a real space. I didn't tell it. The space is real. A real Hubble space. So the scalar product is commutative. And then this 2 is just equal to this because of this formula. So this goes away. So what we get is no. This goes away with this. You have to extract h outside of it. So this remains. Plus 1/2 a h. So this is the original value of the function which we had to minimize. That's the value at x0. And what's the difference? Difference is something positive. That this is always greater or equal than the original value. And it's equal if and only if h is equal to 0, because the expression AHH is strictly positive, except if h is 0. And that's the whole proof. Well, let's give a simple example of a more infinite dimensional situation which we have to minimize something like that. Integral over 1 over from 0 to 1 u x square minus 2 uf dx, where u is equal to u of x is a function we look at, and f of x is a given function. And ux is just the u prime. And you have the boundary conditions. U of 0 is equal to u of 1 is equal to 0. This is the simple equation of the equilibrium of a hanging string, heavy string, in the field of forces which are given by F. For example, if F is constant, then this is just the gravity. Or if the string is not homogeneous, then this F will be the density of the mass. So what's now A? If you make a partial integration here, then you get here this operator now A is equal to minus B over D squared, the operator of the second derivative. And its inverse can be in concrete case computed in two ways, just by solving the differential equation, if you have a simple function f, or by the Fourier method. These are two possibilities to do it. Let's not forget one point here. In almost all of such cases and physical applications, this quadratic equation is an approximation of a nonlinear one. But the approximation was made before you put up the equation itself, in doing the model. When you put up your string and take Newton laws and then use which approximation? Well, that the u of x is small, not too large derivatives. Okay, that's so much as a detour. Now let's go back to this situation here. So we know that if this matrix G, whatever it is, has full rank, then we would have a unique solution. G should have a full rank. It has to have linearly independent columns. G typically has much more rows than columns. Of course, in the finite dimensional situation, you will have to solve system of linear equations with a matrix which is symmetric and positive definite, for which, for example, the Koleski method is a good method to use. Okay. You may have some data at some points here which are more important for you than others, so you will attach to them some weights. For example, it can be just as this point is a result of many measurements, 5 of them to the same point. And you take number 5 as a factor to it instead of summing up so much. So you would have then, instead of this, some, yes, some Wi greater than 0, which we call weights. There is no loss in generality to assume that their sum is equal to 1, but there is no need for that, because minimizing the factor is irrelevant. So now you will have, instead of matrix G, instead of this, would be now or that is then v1 half times x1 1 times xn1. Well, W is just a diagonal matrix with small w's on its diagonal. So in this case, you will have to minimize W1 half G minus yes. Which leads then to the equation A G, excuse me, A Z equals to equals to F, while A is equal to UTWG and F is equal to GTWB. Well, this matrix is again positive definite, which can be easily checked with the same conditions as this here, because the matrix W is itself positive definite because it has positive weights on the diagonal. So we end up again in looking at G as deciding on positive definiteness. Well, the same or similar problems are to fit a polynomial y is equal to ax squared plus bx plus c to the points x1, y1, xn, yn, where we will ask wi sum axy squared plus bxy plus c squared to be minimum. Or so polynomial or a plane in the space A x1 plus b y1 plus c minus z1 excuse me I is minimum. You have none of the points in the space which are fit by a plane. So in first case we have the matrix in every case you have to fit three parameters, although this is in the plane, it is in the space. You have A, B, and C. So now your G will be either x1 squared, x1 1, xn squared, xn 1, or x1 y1 1, xn yn 1. And again, you will ask yourself, when this matrix has a full rank. This matrix G, it is a generic name. It means geometry. It describes the geometry of the situation. See, when this rank will not be full, well, if you make a simple calculation, then you will see that that will mean that the points are all of points lie on a line. And here again, you must have at least 3 points define a line, define a plane. So if they are on the same line, they don't define the plane. And then the rank would be, if none of them are such, that means all of them lie on a line. So it is a simple geometry which tells us that when these G's will be full rank. Okay. There is one more practical feature which we should mention here, and this is the following. Once you did your approximation, you had a point, be it for a line, or for a polynomial, or for a plane, or any other hyperplane for that matter, you will always ask yourself, well, I have the problem of G, Z minus F minimum. And you found the solution. Well, that's not the end of the story. If you would look, for example, at your problem with a string, then that would be the end of the story. With a string, with any mechanical system, you look for the minimum position. Once you have found it, there is no question anymore. But if you are approximating things, then you may ask, how good is my approximation? How good is ELS approximation? So what we have to do, we have to look how large is this expression taken on your best point. If it is very small, then we are good. If it is big, then we are not good. But what is good, what is small? You have to measure this expression in something of the same kind. So a possibility would be to divide this by this. We can write down this in the following way. G is G0 minus F index W over F norm index W. We have introduced a new scalar product in the space defined by the matrix W. The matrix W is positive definite, so that means that this is a bona fide scalar product. And it's not unnatural to change your geometry according to the weights. Okay. Now it has the same, if so to say, the same kind of values. For example, if those F is something which is measured in meters or in kilograms, then dividing it by this would give you a dimensionless quantity, but it would have a meaning without any unit. That's the first point. Okay. But there is a geometric interpretation of minimum distance. See, what is G Z? If Z is running over the whole space, this is a manifold. Huh? This manifold in this case has it is typically not equal to the whole space. So minimum of the distance to the manifold is what? What is the place of the minimum? The place of the minimum is the projection, orthogonal projection to this. This is orthogonal. On the space what? Range of G. If G is running over the whole space, GZ is running over its range. But that's quite natural. If F is in the range, then we have solution of the equation in the classical sense. If not, then our solution is the projection. Well, the solution is not the projection, but the G times the solution is the projection. But this gives us some information now. How big is this? the projection, the size of the projection is always less than the size of the original. So this is always less than 1. So this is a natural measure. The measure goes from 0 to 1. If the projection has yes. So what's the best? What is the best thing? If this is equal to 0. And the worst is of course 1. Well, in this case, your vector is just not tall enough to the plane. There is no reasonable approximation for it. So you see, the geometry is always a very good and excellent thing to look at things, whenever you can do that. So we put our problem quite independently on its geometrical interpretation. This special case, yes. But here, for example, the geometry is not seen explicitly in the problem. But here, it is seen always. Let me now just mention something about those two, some marginal remarks. You see, the people who do statistics are worried about something like that. You have the data which are somehow okay, but there is something which is quite far away. Well, then this method of least squares would exaggerate this fact, because it would square this difference. It would even more put would put too much weight to this one point. So it has, in some applications, it is really very important to have this. This is called sometimes L infinity approximation. This is called L1 approximation, and this is then called L2 approximation, according to the Banach spaces LP, which come in. While the least squares is a matter of teaching almost in elementary schools, the L1 and L infinity minimizations are a matter of serious research until today. Also, a matter of serious research is the subject of nonlinear least squares. That is, you take here squares, but your function which you fit does not depend linearly on the parameters. The function here is polynomial. It's not linear, but its dependence on the parameters to be optimized is linear. But if you would like to fit, for example, such a function, e to the ax b plus c, according to points x, y, y, y. Then you get, when you differentiate this, you get non-linear equations to solve. And that also may be quite tough, even in the simplest cases. I have recently had a paper in my hands looking to minimize such a simple function depending on 2 or 3 parameters of exponential type. Typical, of course, exponential function is a typical function to approximate, and also the so-called logistic function. So it's something like that. It's also a combination of exponentials. I will not touch this problem of nonlinear least squares. Of course, there you have to look at Newton's method, for example, or its modifications, how to look at the minimum. You must first of all then see nonlinear. Are there many minima? Which is the best one? And so on and so on. All of this is non-trivial in the case of nonlinear least squares. And the problem, the linear least squares, there the number of variables, A, B, and so on, goes in millions. While with nonlinear least squares, you are much more modest. And of course, your goal is different. In such a problem, let me write it down. Sum R I B E A x y plus c minus y I squared equals to minimum. So you have some function for I. In doing that, you are concentrated on a very concrete form of function, and then when you find the best approximation, you will apply it for many, many times, so to very accurate, and go very accurate solution for this simple case. So,
can this simple case be linearized by logarithmic? By using a logarithm function?
yes. You mean here?
Yes. You transform the xy and xi and yi by using a logarithm function.
By doing
on y.
Oh, but you are given xy and yi, and you have to determine b, a, and c.
Yeah, but this is
I'm hearing very badly, so please tell it in Croatian. Tell it in Croatian.
Znači, jel se može samo prebaciti, mogu napisati na...
Da.
Mislim, to smo radili na...
Aha.
Znači, ovo tu i je jednako
Aha.
ovo može se c prebaciti na drugu stranu, onda i onda uzeti logaritm. Znači, isto bi log b
Ok.
plus ax je jednako log y minus c.
Yes. Okay.
I onda je to
The
kao...
simple trick
Yeah.
in this. Yes. Okay. Yes. Yes. So in some cases where the exponential function is given, then you make non-linear matters are sometimes solved by a simple trick.
Yeah.
Not only here. So, thank you, and we will make now a pause of 20 minutes.